Hey yo, what's up guys? Baby Bear 4812 coming at you one more time with what I think is a toughie today actually. It's problem 222, count complete tree nodes. I didn't enjoy this one at all. It's a good problem, it's medium. I think it has a shout to be a hard. Again, not all too popular, but Google and Bloomberg have asked it recently. So I thought it might be worth going over. The problem states that we're given a complete binary tree. Okay, that's the key here. Not a binary tree, but a complete binary tree. And we need to count the nodes. Um, really simply, they gave us the definition as well. In a complete binary tree, every level except possibly the last is completely filled. And all the nodes in the last level are as far left as possible. So it can have anywhere between 1 and 2 to the power height nodes inclusive at the last level h. We'll dive into that a bit. But I think the example is easy to understand. This one is a complete binary tree because every level is completely full except for the last one, which may or may not be full. So this one could have had a 7 here as well. It didn't, but it's still a complete binary tree, and it's filled from left to right in that final row, and that's why it's complete. So you may think to yourself, if all we got to do is count it, then we could do like a standard depth first search or breadth first search, and you'd be right. There is a really trivial, I guess in this case it's a brute force solution. It's still linear, where you could actually just go ahead and count all the nodes through like a DFS. And I think you can do something like just return 1 plus self.count nodes of root.left, plus doing the same thing for the right side. And you're only going to do that if the root exists, else you're going to return 0. And I think that this one line of code will run the problem linearly. As you can see there, you can get it done, and that would take like O of height space, because that's the maximum number of calls you'd have. However, would be nice if life were that easy, wouldn't it? Because that is obviously it's a suboptimal solution to this problem. I say obviously it might not be so obvious, but it is suboptimal, and the reason it's suboptimal is because we are not taking into account the fact that it is a complete binary tree. So we can then think to ourselves, okay, what's the difference? So the difference in between maybe a binary tree and a complete binary tree is with the complete one, we have some information about everything except for the last row. Meaning I know how many nodes I have in this tree. I can calculate that really easily. And I can do that for everything, again, except the last row. And that's where it gets a bit tricky. So let's look at maybe a bit of a larger example where I've drawn a complete binary tree from 1 to 10. The depths we're going to label as being 0 index. So the root itself is depth 0, then we got depth 1, 2, 3, and so on. We can ask ourselves, in every given row, how many nodes can I possibly have? So in the first or the 0th row, I can have 1. In the next one, in the first, I can have 2. In the second, I can have 4. And in this one, guess what? I can have 8, and so on and so forth. The general pattern here is that in any given row, I can have up to 2 to the power d, so per row. That means that everything up to here, so let's say we've got, I'm looking at this tree, and I tell myself, okay, this tree has a depth of 3. Again, we're going to be using 0 indexing here. This tree's got a depth of 3 all the way down. I know how many trees I have here. I can, up until the second last row, I know for sure how many I have. And that total is actually going to be the following. So maybe we can write this out. In this first row alone, I've got 1 item. If I add these 2 in there, I've got 3. If I add these 4 in there, I've got 7. Okay, you can see the pattern here potentially that's emerging. In the next one, we would add 8, so we'd have 15 if we had more rows going down and so on and so forth. So the pattern we can gain from this is actually that we have 2 to the power d minus 1 total nodes. And I'm going to put in brackets, not including the last row. Not including the last row. So up until here, if we've got a depth of 3, up until depth of 2, we've got 2 to the power of 3 minus 1 total nodes. 2 to the power of 3 is 8, minus 1 is 7. We've got 7 right over here. So right away, this problem actually boils down to saying, take the total amount of nodes up until the last row, which we can do. That's this simple calculation, plus whatever is left in this at the bottom of in that last row. And so I'm not going to jump into the code just yet, but really at the end of it, it's like, imagine this is our function that does all our wacky stuff. We could literally just return something like 2 to the power of depth minus 1 plus, and then here we're going to have to plug in that value of how many nodes are in the bottom row. And the trick to figuring out this question is actually determining how we can count that number in faster than linear time. Okay, faster than linear time. So we can't do it in constant time, but can we somehow leverage the fact that we've got a binary tree, and B, the fact that it's complete? Can we somehow leverage another search method that's more optimal than the linear one? The answer is yes, we can. And the one that you may be thinking of, which is faster, would be using a binary search. And so we can then ask ourselves, like, well, how do we possibly use binary search here to actually determine how far along we are? And not how far along we are. That doesn't really make any sense. But how far along this bottom row do we actually have any nodes? And I'd invite you to maybe start by thinking of this in the following way. So first things first, even before we do this, maybe I should say we're going to need to find the depth of this entire tree. So we're going to need to get the depth of this thing and notice that it's 3. And so we can spit out the 2 to the 3 minus 1 will give us a total node. So what we will do is, and I was thinking kind of for this video, maybe I'll jump a bit between the code and the description, just so I think there are a few concepts we're going to introduce here, and I want to be able to fragment them a bit. I'll put the standard error checking here, so we'll say if not root will return 0, and then we'll have to say depth is equal to self.getDepth, and we'll pass the root in. So I'm not going to define this function yet, but really simply at some point we're going to have to write a super quick function to just tell us how far down we go in this tree. So we'll pass the root, and we'll kind of leave this for now. This is going to be one step. It'll be our preliminary step. After we've done this, then we need to ask ourselves, okay, how do I now deal with this bottom row over here? I'd invite you to think about the bottom row in the following way. This is at least kind of what did it for me. I almost pictured this bottom row as an array, if you will. And within this array, I would have, 1, 2, 3, 4, 5, 6, 7, 8 possible entries. And I'm not going to be making an array. Okay, this is more just kind of think about it abstractly, because I think that it might help in understanding. Maybe I'll just put none here, none. How we're going to go about implementing the code. Let me make sure I've got 8 here. Make this an n. 3, 4, 5, 6, 7, 8. Okay. What if I could ask myself the following? Well, when we think about binary search, typically we think about, we've got a beginning of the search, a left and a right, or maybe a high and a low, and then we calculate a midpoint. So what if I told myself, let me check if the middle of this length here actually exists? So I know that if I was to think about this as an array, this would be index 0, and this would be 2 to the power of d. So we've got 2 to the power of d items per row. This is our depth 3, our row 3. We've got 2 to the power of d, and then minus 1 would be the index. So this would be my right pointer, this would kind of be my left pointer. And now I want to ask myself, does the middle pointer exist? And that would be, I guess, one of these two. So I think it would be this one. What if I ask myself, does this exist? And we'll actually figure out how to check whether or not this exists. This is going to be the next step. But hypothetically, if I could ask myself, does this exist? This would kind of refer to this right over here, where we have a none. If I told myself this does not exist, well, then in that case, what would we actually have to do? Well, if this doesn't exist, then I'd have to bring this pointer down here and say, okay, then we've only got to start checking in this section now here in this lower half. And if it does exist, then I can start searching in this upper half and looking for kind of the node that I want. The trick here is going to be to return the how do I put this? Okay. Let's say this is index 0, 1, 2, and 3. Okay. If I was to do my binary search, and when I do, I will end up with my left index pointing here, and my right index, let's say, will point there as well, or my right index will be 1 over here. If I was to return this left index, that's index 3, what does that tell me? Well, if my left index here is pointing at the first not available node, it's pointing at index 3. If I return that index, that actually tells me exactly how many nodes do exist. Since we're filling in from the left to the right, because it's a complete binary tree, well, that means that if I return this index 3, everything before that, 0, 1, and 2, must exist. Because I'm looking to get my left index onto the point where, in fact, it's kind of the first non-existent index, if you will. And again, I hope this doesn't cause extra confusion with the array. Let me know in the comment section down below if it does. But just in terms of actually thinking, jumping down this tree to figure out where our last item is, or our first non-existent item is, that's how we're going to return exactly what length we have in this bottom row. The one thing I haven't addressed, which I will do, and I think I might do this as we're coding it out, will be to say, how do I actually decide if I'm sitting at this root here and I'm interested in looking at, let's say, this index over here, how do I get there? Like, how do I decide if I take a step left and traverse this way, or do I take a step right and try to go another way? How am I actually going to make my way down the tree? Interestingly enough, making our way down the tree will be a logN operation, and actually choosing, moving this left and right. Let me do this. Moving this left pointer and moving this right pointer inwards until we find that final node. That is also a logN operation. So what I think makes this problem really tricky and not common is the fact that for each one of these logN operations, we're going to have to do another logN operation, which is traversing down the tree. And so we're going to have the logN times the logN, which is a log squared and time complexity in this problem. And again, I think that's maybe what makes this a bit of an not awkward problem, but again, I think it's one that's uncommon. I at least haven't done this. I've done something like 350 problems on Leetcode, give or take. This is the first time I've used a binary search within a binary search. So for what it's worth, that's why I think this one is a bit tough. Now, I've kind of talked about roughly how we're going to determine how, what length we're going to return, and when we finally pop out of this binary search here, we're just going to return the index that our left pointer was at. That's pretty common binary search stuff. But how do we actually determine which route we're going to take? For this, we're actually gonna write a separate function, and again, I'm just going to do something here. I'll say something like define node exists, and within this node exists function, we're going to have to do some sort of traversal from the root all the way down to the bottom, and at every step along the way, we're going to have to determine whether we're going to go left or right. The way we're going to determine whether we're going left or right is in essence just going to be saying, let's look at the index that we have right here. So if this is my mid index and I want to make my way down, what I'm going to do is I'm going to say, let me pass in that index into this traversal function, to the node exists, which will walk us down the tree. I'm going to pass that in, and then with every step along the way, again, I'm going to have my left and right index. I'm going to have the one that I'm looking to get to, and I'm essentially going to say if the middle of these two, if it's less than or equal to, the mid is somewhere here, if it's less than or equal to the index that I want to get to, then take a step left. If it's greater than, then take a step right. Because if this index, if I'm, let's say I tried to get to this index hypothetically, it's going to be on the right half of the tree. So I'm going to have to take my first step to the right. After my first step to the right, I'm going to have to determine is my index even further along from the respective middle of the tree, if you will. If it is, take another step right. Otherwise, take a step left. And that's how we're going to sequentially take steps left and right as we're going down the tree. I think that was a bit of a mouthful, and maybe the explanation was a tiny bit all over the place. I do think it will make more sense when we get into the implementation, and reviewing it a couple times over might be necessary. Again, at least it was for me. I found this one really tough to follow along and grasp the logic on how to do it. So for what it's worth, that's where that's at. I hope that explanation made sense. Let me know in the comments if you have any questions. But until or not until then, but for now, let's jump into the code and see how we can actually implement this. So I'm going to move this over, and I'll start by saying the following. So we kind of did our error checking here briefly, and I said we're going to need to determine what the depth of this tree is for sure. That's going to be relatively straightforward. We're going to set a depth variable. We'll set it to 0 initially, and I'll return the depth I'll return depth at the end of things. And then what we'll do is we're going to do a simple while loop where we're just going to say while root.left exists. So meaning while we have another layer down, and I'm going left because again, it's a complete binary tree that's filled from left to right. While there is another level to go down, increase the depth by 1, actually move me down, so make root equal root.left, and that's it. And at the end of this, once we get to the final stage, there's not going to be a root.left anymore. We're going to return whatever depth we had, and again, that depth is going to be 0 indexed. So I'm going to minimize this for now just so it doesn't take up space again. I think the code here is pretty simple. I'm not busting any brains here with this operation. After we find this depth, I would kind of say maybe it makes sense to do one more quick bit of error checking. We're going to say if the depth is 0, let's just go ahead and return 1. Meaning depth would be 0 means we just have the root node and we're not going any further. So that'll take care of a couple of edge cases for us. Now, in this step, this is where we're going to do our binary search to find the first null nodes index. And the reason we're looking again for the first null nodes index is because if I find that this first null nodes index is 3, that means that I have exactly 3 items preceding me which are not null. Okay, and that's why we're going to be looking to do that. And so for typical kind of binary search of this final row, if you will, we're going to set left equal to 0 and right is going to be equal to 2 to the power of depth minus 1. Now, just to make things clear, 2 to the power of depth minus 1 isn't necessarily representing the same thing here and here. 2 to the power of depth minus 1, or rather, in this case, 2 to the power of depth minus 1 equals this. It's the total number of nodes, not including the last row. Here, in our bottom row, which is at depth d, we can have a total of 2 to the depth or 2 to the d elements in that entire row. So if we're indexing them, the first one can be at 0, the last one can be at length minus 1. So that's why we're setting it to 2 to the power of depth minus 1. Now, this is where we're going to jump into our binary search, and we'll do this while left is less than or equal to right. And so while it's less than or equal to right, I'm going to call this, I could call it mid, but I'm going to go ahead and I'm going to call it index. So remember, the reason I kind of did this diagram here, and again, I know I'm never creating this into an array, all right? But what I am doing is I'm almost thinking about it like an array where the index is that item, that specific node that I'm interested in that I want to search for when I'm going to be doing my traversal down the tree. So I'm going to call it index, and instead of doing something like right plus left divided by 2, which would give me the middle. A really common trick just to avoid integer overflow would be to set it equal to left plus right minus left divided by 2. And I've kind of talked about this in other videos, and I'd encourage you to see why this is equal to right plus left divided by 2. If you go ahead and expand this fraction, or even expand this one and work backwards, you can turn it into the other one and see why that works. Since we're subtracting 2 numbers here, we're subtracting a smaller number from a bigger one. That's going to avoid having an integer overflow, which we could run into if both right and left are really, really big here. So semantics, but still worth mentioning. We can now ask ourselves, and we haven't written this function yet, this node exists, but I'm really curious to know if this node exists. So if this index node, so if self.node exists, then we can pass in the index that we're looking for, as well as the root of the tree and the depth of this tree, because that's how many steps we're going to have to take down to actually get to the bottom of this tree. If it does exist, so imagine I was kind of looking for, imagine I was searching down and I found this node, and I checked for whatever reason this node that got me to 10, and I said, okay, this exists. But what I'm interested in is the first node that does not exist. So on my next search round, I want my left pointer to be here. I want it to be 1 over in hopes of finding a node that does not exist, the first non-existent one. So I'm going to want to set left, or actually, I'm going to have to, we're going to set left is equal to index plus 1. And ultimately, because we're doing this, the last number I want to return is left, where again, if left in this case is 3, that means there are 3 items before me, so I want to return all the nodes I've had so far plus the 3. Now, otherwise, if this isn't the case, then we're going to have to check the other side of things. And so we're going to set right is equal to index minus 1. And I'm going to delete a bit of space here. The reason we're checking right is equal to index minus 1 is because by default, our left pointer is always going to be pointing at a node, no matter what. It always will be. And so if we ever get to the point where I'm somehow I've got, maybe I've gotten to the bottom of the tree. Maybe all I've got is 1 and 2. And somehow, or not somehow, but I've got my left pointers pointing here, and my right pointer is also pointing here. Okay, they're both in this binary search. They're both pointing at a node. This is what our index is going to equal to. And when we traverse down, we'll say, okay, I found this node. It's only when I find a node that I'm going to say, okay, now let me take my left pointer and move it over by 1, because again, I want to find that first non-existent item. So that's why we're setting right equal to index minus 1, okay? Because I want to make sure that that right will be pointing at something eventually, so that when they match each other, when left and right are equal, and we set that as a condition here, we're going to keep doing this as left is less than or equal to right, we can then take this left item and left index and move it up by 1 unit. All right, so that's going to be this binary search here. And the part that we still need to fill in is whether or not this node exists. So this is going to have to take a self argument, and this one is as well. I think I've forgotten that. So it's going to take self, and we said we're passing in index, we're passing in root, and we're passing in depth. Now that we're jumping into here, we're once again going to have one more binary search that happens. That's aggressive. Left is going to equal 0, and right again is going to equal 2 to the power of depth minus 1 like it had before. So this binary search we're going to implement slightly differently, because we know exactly how many steps we're going to need to take. And every time, actually let me put it this way, this function is going to be walking down our tree. It's going to be at any given point taking either a left or a right step and getting us down to our leaves. The amount of steps that it's going to take is going to equal the depth. So for some amount of operations or some variable, I'll leave it at the underscore, in the range of depth, let's think about it. If this tree had a depth of 3, we're going to have to take 1 step, 2 step, 3 steps to get to the leaf nodes. And so that's why we're going to go for while we're in depth. I'm then going to calculate a midpoint of these, and I'll calculate this the same way with left plus right minus left divided by 2. And then, so how did we say we're going to do this earlier? We said that we would, depending on whether our mid was less than and equal to or greater than our index right over here, we'd either go left or right. So we said that if mid, if our index was less than or equal to our midpoint, then we would have to move left. So we'd have to say root is equal to root.left, and we're going to have to change one of our variables. So we're going to have to do something then about our right variable, and I'll deal with that in a second. Otherwise, if that's not the case, we're going to have to go to the right, and then we'd have to move our left variable. And I'm leaving these as a blank just so we can kind of talk through what it is that we're going to do. Eventually, when we've done this, we're going to return the root point that we're at. This leaf, if it's a null leaf, we're going to return none. And when we get here, this condition will say false. So we're not going to be moving our left index up by 1. If it does exist, however, if it's anything that's not none, then we say we found one. Let me move my left index 1 over to see if I can make my way to a null node. And that way I'll ultimately return everything before me, or the length of everything before me. Now, if our index is less than or equal to the mid, then we said that we're going to have to take a step left. Okay. Our right index then is going to have to become equal to mid. Okay. So let's think about it this way. If I'm taking a step left over here, I'm now going to have to look at this section over here, and this was ultimately my midpoint. Since I'm interested in this now, my right's going from all the way there until the kind of the maximum possible point that I can traverse that, given that I'm on this half of the tree. That's why right's going to mid. Conversely, then, if we're going to the other side, left is going to have to go to mid plus 1, so we can jump it over and look at the right-hand side of the tree. And this should be it in terms of the code that we need to solve this problem. I'm going to give this a quick run and just make sure that I haven't made any mistakes. And I made one on line 14. Said mid is equal to, oops, I didn't mean to do that. Left plus int object has no attribute, right? So what did I do here? Index root and depth. This on line 19 says root is equal to. So what happens when I talk too much and I don't code enough? Okay, I'll press submit here. Okay, and it works. So I wanted to make sure it works before I do a walkthrough of or like the summary of the solution. So this was like I said, it was a bit of a toughie. It ran in log n times log n complexity, which is log squared n, and same thing with space complexity. I will point out that that is still better than that is still better than linear time. It's quite a bit better. It's exponentially better. I'd invite you to check out, either you can kind of solve, I won't get into, but either you can kind of solve this problem using calculus by kind of checking what the graphs would look like of log squared of n versus n, and then you'll see that it kind of tapers off and gets exponentially better as you go on and the numbers get really big. But to summarize what we did after error checking, we said we're going to need to determine what the depth of this tree is. The reason we're going to have to determine the depth of this tree is because that the answer we're going to return is going to equal 2 to the power of depth minus 1, which is the total number of nodes before our last row. And then really where the bulk of this problem was in determining how many elements are in the bottom row of our tree, how many leaf nodes there are, if you will. The way that I kind of pictured it, and I hope this analogy didn't confuse anybody. I hope it helped more than it confused, but I almost thought about indexing these like we would in an array. And sorry, I don't know why I switched there. And ultimately, if I return the first index that is a null index, then that tells me exactly how many items were before me. And that's what we were doing here. That's why we return the left index after this binary search. This function that we called this node exists function was a bit of a clever way to do a walkthrough and a traversal down the tree from the root down to the node that we're looking at, the node that we indexed, if you will. Again, I'm putting that in air quotes because I'm not really indexing. I'm not putting these in an array at any point. But I thought that was kind of the easiest way to think about this problem. If you're still a bit confused, try to watch it over, try to draw out the example yourself. Again, maybe I'm just projecting because I struggled with it, but I think this one was tough, and it definitely takes a few repetitions to get it. I did hide this function originally just to save some space, but there it is, all the code in its glory. Let me know if you guys have any questions, comments, feedback. Like, comment, share, subscribe, all that good stuff. Really appreciate it, and I will see you guys in the next video. Peace.